So my name is Jeff Hilland. I have the privilege of serving as president of the DMTF for a number of years. It's a fun job if you like that kind of work. But I'm also a distinguished technologist in Hewlett-Packard Labs. Between Brett and I, we co-chair the SPDM working group. Used to be a task force under the PMCI working group, which is, we developed a model in DMTF where we can spin stuff up basically in a week or two to get a standard going. And so real happy we were able to do that. Quick disclaimer, there's some stuff in here that's going to change. I can almost guarantee something we're going to say is not going to be the way things are at some point, because that's because we're hitting a moving target. So when I talk about the past, that's pretty straightforward, but the future, well, nobody has an accurate crystal ball or we'd all be rich. Quick background on SPDM. How many people know of SPDM and have like read the specs or something? So a majority, but not everybody. We're going to go into SPDM for storage binding. This is SDC, so that's one of the new specs we're working on, and then we'll talk about post-quantum and how we're going to deal with that. Most of you in here could probably draw this slide for your managers. Don't bother. We've got it out in PowerPoint form somewhere. Really, it's like, as Eric was saying, the threat landscape is pretty broad. Most of this stuff we have seen inside my company of some form or fashion. Somebody putting a probe in where they shouldn't, or putting in hostile firmware, supply chain changes, things accidentally falling off the truck between when they left the supply house and when they made it to the manufacturing floor. All those kinds of things are very real threats. We started with a nice root of trust. I know my company makes a silicon root of trust, and that works great, but how do you deal with the rest of the platform? And that's where SPDM was born. Going out and trying to figure out the attestation and be able to validate the thing you're talking out there to is in fact what it says it is, and that nobody in the middle is trying to screw things up. So that was kind of the point of SPDM, was to extend that root of trust to the whole platform, because if you can't trust the platform, you can't trust any of the software or anything else you're loading on top of it. So really, why SPDM? That was exactly what I just said. The industry needs a common solution that works for the control plane as well as the data plane. And I'm a control plane guy. I used to be a data plane kind of guy, moving traffic back when I did InfiniBand and RDMA, but then we started concentrating on the control plane. And I've got a few slides on the end of what all this means to that magic bus that's inside the platform. But as you look at the rest of everything in the infrastructure, your control plane widens, particularly as you're, depending on the quote-unquote platform you're delivering. When you're talking, rack scale or data center scale or trying to do a storage fabric or the rest, we've kind of got that in our charter too to make sure that's taken care of as well. And of course, the industry standard, there's a couple of things that are up here. There's also some things that aren't, and mostly it's around libSPDM. When we started doing libSPDM, we didn't plan on people using it to the extent that they are. In fact, DMTF had a policy for a while where we were just doing sample code, and the board looked at that last summer, I guess it was last March, and rolled that policy and said, you know what, we really are doing open standards and open source that are product grade. Come in and help. The water's fine, please pick up a pen and type away and help. But let's not shy away from it. Since then, we've seen about 2,000 clones a month of the libSPDM repo. Now, how many people are there out there trying to create protocol infrastructure? And so we're seeing 2,000 unique clones a month, and I think there have been about 12,000 clones of libSPDM. So Redfish, everybody heard of Redfish? The Redfish tool set, we see about 50 a month. And that's customers that have access to that. So it really kind of, to me, is something that's very telling about what the industry is doing with libSPDM. libSPDM is about a year behind the specs. They're doing a pretty good job of keeping up. And they certainly are a good quality control source for us as far as, gee, what did you mean by this? And these are guys in the room with us when we wrote the spec. And they're, well, it's funny. You're sitting in the room and one person says something and you think they said this and you've internalized it this way the whole time. And it turns out when you start paying attention to the piece of paper, things might be a little different than what you intended. So glad to have them on board. Basically, all of SPDM features fall into one or two main goals: device attestation and authentication, and then secure communication over any transport. And now there may be features and functions you need, and we've added them over time in order to achieve those two goals. But it really took about until 1.3 for us to finally get everything working the way we wanted to. And so, that device attestation and authentication is really the ability to verify various aspects of the device. You'll see measurements in there, and that measurement can be anything from configuration settings to silicon to firmware loads to workloads, anything you want. And I'll talk about some of the numbers we're seeing there in a minute. And then secure communication over any transport. And it was kind of exciting when PCI and CXL and those people started looking at SPDM and said, well, gee, as a device vendor, I got to put silicon down there to deal with, the management side of this. Well, why should the data plane be any different? So it's good to see that the protocol is being used for both of those. Certainly optimizes your footprint in your silicon solution. Features over time, when we started 1.1, we really were, working on just secure session. 1.0, we were just doing measurements, device attestation, and authentication. It was just, measurements and certs, and that was kind of it for 1.0. And then in 1.1, we did key exchange. And we thought, hey, great, we've got a complete solution. No, it turns out you're not even close. So we had to do 1.2. And, as we're doing 1.2, we're hearing people listen and looking at 1.0 and 1.1, and we're getting a little bit of feedback as people were trying to do it. Implement it, and so you'll see a couple of errata versions of those as we go along, especially through the years. Right now, we're maintaining every version of SPDM backwards compatible, and we're doing errata on all the existing versions of the spec. At some point, that's going to stop. I'm not going to tell you when, but you'll hear from us when we decide it, and it'll work through all our industry alliance partners, because we'll go, this is what we're doing, is it okay? And if we get a lot of feedback, we'll do what the industry needs to. 1.2, we started doing, installation of certificates. Turns out all our factories had a slightly different process for landing those certs. Gee, we're all doing it, why shouldn't that be common? Allow for alias certs, right? Thank you, TCG, for giving us 2 certificate models. And then, of course, when it came to 1.3, we added a third one, which was generic. So if trying to keep those devices around for a while. We added a bunch of algorithms in 1.2 as well. And we added large message support. Turns out people were getting a little creative with some of the SPDM messages themselves, especially with opaque data. We didn't really plan on the messages getting that big. More on that later, because PQC does a number to us. And then in 1.3, we added eventing, multi-key, the generic certs, MEL and HAM, the measurement event logs, and the hash extended measurements that really give us that longevity to the measurements that we're trying to do, where you can kind of watch them as they change over time. And then endpoint info, we started out doing MCTP and thinking, well, I've got all the MCTP and PLDM stacks. I can look at through data. I can do all that kind of stuff. Well, again, if you're a data plane, maybe somebody's getting there before the PCI enumeration happens, or some other kind of bus. So some other protocol where you don't really know yet. SPDM has to be the first thing in there. We added endpoint info for people that can't get it any other way. Bindings that DMTF does, we've got MCTP to SPDM. That was our first one. And then we broke out secure messages and secure messages to SPDM. We took that secure message and broke it in half so that MCTP could use this part, but we'd have a common payload for anybody doing things over PCI or CXL. So we tried to do as much of that common framework on the bytes on the wire to help people that are trying to cast this in silicon leverage it. Then we did SPDM over TCP. And there's a comment on LinkedIn now. It's like, don't you think that's encroaching a little bit on TLS? It's like, well, if TLS did measurements and could, tell me everything in my rack, and, I'm doing rack scale architectures where I've got management and control planes and little thingies sitting inside the box, and I'd like to expand my root of trust beyond just the platform to the entire infrastructure. If TLS would pick up that charter, we wouldn't need to. But, I wouldn't expect them to do. Entirely different data point, right? We looked at, when we did the protocol, and we kind of broke things down in very slow and simple steps that were easy for silicon to adopt to and small footprint devices could handle. TLS is designed for, thousands of users going on simultaneously. And that wasn't the use case we were after at all. And then Brett's going to get here and talk about the SPDM for storage binding here in a minute. In fact, right now, because I think that's the next slide. So at that point, we hope with all our industry partners we'll have kind of everything. But if you hear of something, yet another binding that isn't being done by someone else and that somebody needs to do, let us know. And without further ado, Brett?
All right, well, thank you. I'm Brett Henning. I'm a security architect at Broadcom. And I was going to go through the SPDM storage binding. So as Jeff mentioned, this is a new binding. It's actually quite new. There's a work in progress version that was just released, just a couple weeks ago, in fact. So it is out there for public review. Please go look at it. I was going to go through just what are the highlights of that spec. So first of all, why are we doing it? Why are we doing a storage binding? Well, SPDM was really focused on the devices in the server at the beginning, and that was really good for things like the NIC and the storage controller and DPUs, right? All these things that you want to test inside the server. Problem is there's a couple hundred hard drives sitting out there, and no one's actually checking on them before you spin them up and use them. So there was a request from a number of people in the industry to really go out, to really give us a way to talk to the hard drives. When we started taking this on, one of the things we wanted to do was make sure that we had parity between the three main transports that are out there, right? SAS, SATA, NVMe. And I know that NVMe has some ways of getting at attestation information, especially when it's connected over PCIe, but there was nothing for SAS or SATA. And really NVMe was kind of spotty, right? There were a lot fewer ways of going after fabric attached devices than there are for direct attach. So basically what we wanted to do was extend SPDM over these transports and do it in a consistent way. So how are we doing that? Well, we've created a new binding spec. This spec number is DSP 286. If you end up going onto the DMTF website, you can find it under that. This leverages a security protocol ID that was assigned. The protocol ID is E8. For those who are familiar with SPDM, this really takes the place of those two early binding specs that Jeff mentioned. So this fills the role of both the 275, the SPDM over MCTP, as well as 276, which is the secured messages over MCTP. So it binds both of those to storage. Another goal is to be able to support newer versions of SPDM without major changes to the binding. There might be minor changes, but we don't want to have to rip and replace it on a regular basis. So how does it work? Well, I'm going to go through a few slides that just cover kind of the theory of operation for the binding spec. It uses the security protocol commands, right? Those exist in every single transport that's out there. Generically, they're just IF send and IF receive. And they all use basically the same structure, right? They use the same layout of command block, as well as the same codes. So these commands gave us a 16-bit field. We were able to leverage that to basically form the basis of the binding. In that field, we put in a connection ID and we put in an opcode. So we're actually basically saying, all right, here's our opcode. We're going to have some other command or some other details follow this. Well, what else can be there? Like most protocols, right, it starts off with discovery. This discovery is specifically focused on discovering information about the binding or about the transport capabilities. This is modeled heavily on things that are very common in the storage world, right? Things like the SCSI inquiry command. So it looks a little bit more like inquiry and a little bit less like an SPDM version negotiation. And that's done on purpose, right? That this fits better with the world that we live in storage. Discovery, right? It's pretty basic, right? You just get back, basically here are all the capabilities of the device. And then it's up to the requester to say, all right, which of those capabilities do I want to use? So the use of IF send and IF receive. We had some interesting challenges in trying to get these to actually work with a protocol like SPDM. So one of the real challenges with this is SPDM is just kind of built around a bidirectional model. And that works well in MCTP, and it works well with a lot of the buses MCTP runs over. It doesn't work well in storage, right? We've all seen the history of bidirectional commands in storage. It never really took off. It's definitely not a thing for the security protocol commands. So instead, we adopted a model that basically pairs up IF send and IF receive commands. So it uses them, always uses them in a pair to send a command and pull data from the device. And we're going to go through what those flows look like. So this is kind of the simple flow. This is how we intend to exchange data for traditional SPDM commands. These are the ones that are found in the 274 spec. And the way the command flow is we'll use IF send to actually send the request. You'll get back a status on that. The status is really just a transmission status. So did the command get there? Right? It says nothing about the ability to process the command itself. And then the host will send an IF receive. So it'll basically say, here's a receive with an allocation buffer, and you can put the SPDM response in this allocation buffer, or this allocated buffer. And so then the device will actually send back the response data in that buffer. So a little bit of overhead, but these are relatively fast buses compared to I2C and some of the things Jeff's going to be talking about. So hopefully, we should be able to get the round trips to a pretty manageable time. So we had another problem that came up, right? As we were going through that flow, questions started coming up. How does the host know how large of a buffer to allocate for the response? Right? It's going to need to go allocate something. This isn't like MCTP where you can just start processing 64-byte packets and just keep pulling them in until the data stops coming in. Right? You have to allocate a buffer ahead of time, and it has to be big enough. Or you have to go back and try the command again. So, we came up with, well, there's probably a handful of ways to do this that are fairly straightforward, right? You can just always allocate max size. Right, that's always a possibility. You can actually build a lookup table, so you can say, for each command, I expect roughly this amount of data. But people really wanted something that was a more predictable way of doing it. So we actually added a command called the pending info command that can basically go down to the device and just say, how much data do you have waiting for me? So this can actually go into the middle of that flow that we showed and go and say, all right, how much data do you have? Now this is considered outside of the SPDM message flow itself. This is really a transport mechanism. But using this command, the device can come back and say, here's exactly how much data I have pending. Single-threaded flow, but that's already an assumption that SPDM the SPDM is built around. So that's not really breaking anything. And then you can allocate exactly the buffer size that's needed, and then go fetch the data. So it gets rid of some of the tri-fail semantics that would go into a couple of the other approaches. Encapsulated flows. This was kind of the next problem set that came up. Typically, so SPDM, yes, it is request response. Typically, it flows from, what would be an initiator to a target, but that's only typical. There are cases where the target can actually initiate traffic back to the initiator. The most common use case for this is what we call mutual authentication, which is really our flow where the requester will go through and it's performing all the attestations, checks on the device, and then the device says, well, I don't know if I trust you, so I'm going to turn around and do all the same things back to you. Well, if we really want to create a complete binding, we have to extend all this to the storage transports, just like we do everywhere else. So fortunately, SPDM already had an encapsulated flow. So it already had a flow that envisioned, well, what if the device can't initiate traffic? And we've actually got a picture of that. It is exactly what you would imagine, right? The initiator, you basically have to go send twice as much traffic or twice as many round trips. But basically the initiator starts off with an IF send and it says get encapsulated request. So it basically says, do you have something for me? And then it will send an IF receive to the device, and the device will say, yes, I have a request for you. Here's the request. And then the initiator has to come back with another IF send and say, all right, I'm going to give you a buffer. And yeah, and then basically end up with an IF receive. Yeah, so it sends an IF send with here's the response to the request that you gave me. And then finally there's an IF receive to basically close out the loop. And the device can actually use that final IF receive to send the next request. Or it can say, I'm done, right? I'm done requesting. So a lot of round trips. Definitely looks a little counterintuitive, but it works as a flow. Another consideration, the transcript hash. So something that SPDM does is it keeps a transcript hash that basically runs from the start of communication all the way through to the end of the challenge command. And the reason we do this is to protect against attackers in the middle, and because otherwise, basically, the protocol would be open to someone coming in and trying to snoop on the middle of the bus, or trying to modify messages and trying to insert things. Right? There's all sorts of havoc you can play. So effectively, what you have to do is, at the end of this big long sequence, both sides are going to say, I have a record of the messages I sent and the messages I received, and they will exchange those, and the exchange of those is itself signed, and basically at the end of all of it, they have to compare. Or else you say something's up and things are rotten, I'm leaving. What we had to do with the SPDM binding spec is we had to come up with the scope of the transcript. Right, that was a fairly important decision. What we came up with is it does not cover the IF commands. Right, the IF sends and IF receives themselves are outside of the scope of the transcript. The transcript only covers the SPDM messages themselves. So all these other things like the discovery, the pending info, these are out of scope for the transcript. Also, if there's any padding, because interfaces like SATA require 512-bit or 512 byte allocation increments. So there's a lot of padding that can be present. We skip all that. The reason that we wanted to skip all this is so that we can enable basically bridging and pass-through. So if you have two sides of an interface, you really want to be able to pass commands from, say, a BMC through an HBA to a device. And really keeping the transcript focused on the just the SPDM messages allows us to do that bridging. See, next thing that we tackled were secured messages. So SPDM since version 1.1 has had secured message support, and basically what that gives you is that gives you authenticated and encrypted message exchange, authenticated and encrypted messages. So we wanted to actually extend that out to the storage transport. Just like, again, trying to achieve parity with the spec. There's a lot of details, but it can actually carry SCSI commands, ATA commands, right? It can carry storage commands themselves as well as SPDM commands. Note, though, this is not meant for efficiency. This is not a high-speed transport. It is not meant for disk I/O. It has quite a bit of inefficiency in it. We're going to show a picture of it. Basically, it's a descriptor-based model. So the message is just built with a number of data structures and number of descriptors that basically point to sub-buffers within one big giant buffer. Definitely encourage you to get the spec and look through all that. And then last thing we took on was status reporting. This is something, it's kind of one of those nitty-gritty details, but it's important to get right. So definitely encourage people to look at it. There's a hierarchy of statuses that we've defined, and it runs all the way from did the transport of the data succeed all the way down to did this stuff down in the data buffer itself actually make sense as a message. And that is it for the storage binding. So I'm going to turn it back over to Jeff to talk about post-quantum.
All right, can you hear me? Great, thank you. So, I think most of you are aware of this, right? In August, we finally got the drop we were waiting for of all the specs from NIST. I know that in SPDM, we started talking all this about March. It was good to see some of the sizes change, particularly down at the level we work at. I don't know if it changed enough for me, but the names I've got to get used to, right? You get so used to calling them Kyber, Dilithium, and Sphinx. I got to get used to MLChem and MLDSA. Pardon? No, the drafts were published in 23, and then bullet 4 says the final ones were in August of 24. So yes, it's right. And I did the same thing when I looked at it again this morning. I was like, wait a minute. Oh, there it is. Okay. That's pretty bad when you write something and you still can't remember what you did. Anyway, there's another PQC signature out there. We knew we had to take that into accommodation as well. And then, we know they're still looking at additional ones beyond Falcon. So we knew we had to figure out that. And then, again, CNSA are expected to make these required. What happens in the EU? What happens in your customer base? There's some that are going to follow. There's some that aren't. So even though we're going down this path, we knew there was a certain amount of future proofing we had to do. So we came up with a proposed plan in March, and we ratified it, and I think we shipped it out in May, and then we shipped out another proposed plan recently, to try yet again, because the original plan was I'm a paranoid kind of guy when it comes to some of the security stuff. I didn't want to be the first one out for SPDM. We weren't the first one out when we did SPDM initially, right? We leveraged other protocols to do it. So I was a little paranoid. I wanted to wait on TLS. Meanwhile, the device people are trying to figure out what to put in silicon, and they're going, no, we're not going to wait. We really can't. We can't afford to wait. So, okay, I get that, especially with the CNSA requirements, right? When you got to get digital signatures done next year, supposedly, and key exchange by 30. My goodness, what an aggressive requirements list. So we came up with this, all right, we're going to adopt PQC for the scenario where public key and then is exchanged as part of manufacturing or whatever, a priori. And then we're going to support X509. Well, that tells you right then, we got to wait on X509 to get PQC in there. And so we're waiting on them. We hear all kinds of rumors of when they're actually going to be done, but we're not. DMTF has a policy where we don't submit a spec out there without a formalized reference where you can actually click on it and get there. So, plus who knows what fields are going to change. Hopefully nothing but, and then the other one was, again, I wanted to kind of wait on TLS to figure out, some of the initial vectors and what are the implications thereof, but some of the folks inside of SPDM have figured out, all right, 800-227 is going to have all the information in it we need in order to support the protocol. And so that's our next plan is not to wait on TLS, we're going to wait on 800-227 because that's got the requirements for ML Chem in it. So, yeah, wow. So I'm glad that wasn't just news to me when they dropped it in our lap because it's nice to see everybody else starting to search. So that's a new document for you. All of this is planned to go into 1.4. And so we work in GitHub. DMTF started this with Redfish back 10, 12 years ago. And doing the specs in GitHub is great. You do all this stuff parallel. And we're doing one pull for signatures and another pull for the key exchange protocols. Meanwhile, we've got all these other issues and pulls going on, and our rule is all that stuff goes to the end of the agenda. If we've got time and you got your pull in it, it's a train model, get your code in, get your thing in there, and we'll do it. If it's not ready, we're not waiting on anything else. The industry needs this. So that's the track we're going on as far as PQC itself and releasing the spec. Well, what about hybrid? If you could show me an industry standard hybrid solution, I would be willing to start another pull in there and treat it simultaneously. There's a bunch of vendor solutions, and certainly some of those vendors have enough weight to drive their supply chains to do a hybrid solution. But I don't know, is it one hash followed by another hash? Is it both of them together? What's the X509 cert? Is it separate certs? Is it one cert? Without all that information, it's very hard to speculate and do something normative, especially with the kind of support we're looking at. And I don't know if I necessarily have this in here. No, I don't. One of the things I really like is, you heard me talk about earlier about the libSPDM adoption. We've had people out, research facilities and people out in the industry go in and validate the code. They validated the spec too, which I thought was cool, but I'm more interested in validating the code. And so now you've got all this validation on the commands we've got. We're going to fork those commands and make them bimodal, where one goes down the PQC. No, see, yeah, exactly. No. Maybe the safest thing would create a parallel set of commands that do the exact same thing, exact same flows, but I can validate the code much easier. And that's what talked me into doing that. So maybe that's what we're going to do. Again, we don't know. We haven't got the things pulled. The spec isn't released, but that's the approach I favor right now, at least. So the libSPDM guys are still busy on 1.3. They're going to be busy on 1.3 to the end of the year. So if 1.4 makes it out before the end of the year, that means all these dependencies got out in time and we were happy. Expect a work in progress as soon as we think things are complete but not done and polished, because we want the feedback and scrutiny of the industry. And whenever we do those releases, you can go to our webpage and hit a feedback portal. We've also got a forum. You can click through the link page for libSPDM and just give us questions dynamically through the forum, and we answer them every week. So there aren't that many questions out there, which makes it easier. But, you know, if you do have questions or feedback on any of those specs, let us know. So what's some of the impact, right? Our message lengths are 2K. We got 2 bytes in there. Well, gee, some of the Sphinx packets are on the order of 48, 50K. And so depending on the data you're actually protecting with those signatures, we're probably going to blow that 2-byte limit. So that's yet another reason to go through a different command set is let's do a different set of lengths as well. We know we've got to extend the signatures. We want to keep some of those initial commands the same because they're not that big as far as what signatures you support, the different capabilities and algorithm discovery kind of things, as well as, I don't know about digest, but you know, things like that. They are parts where the beginning parts of the flow should remain the same. But we know we have to extend those structures. So we'll argue about what the definition of backwards compatibility means when it comes to tacking on stuff at the end, because it's not completely at the end because there's some opaque data and stuff. We've got a version code in the beginning of every field. So your code should be able to handle it, should be fine. That's worked well for us so far. Again. And then, see, I covered all that, and then may need additional algorithms to support PQC or may use a completely parallel set. DMTF has a whole group that does everything on MCTP. My company builds systems. I go back to the original System Pro before there was ProLiant. And I2C, if you look at MCTP, it's a 64-byte packet. By the time you're done the MCTP and SPDM headers and all the rest, we got 51 bytes left. Under 100 kbps, most people. You do 400 on I2C, but almost nobody does it. So really, you end up with about 100. All right, so now I got, if I'm using Sphinx Plus, I've got a 49,000 byte signature on the thing I'm protecting. And if you're using MLDSA, that's around 4K or so. So I did the back of the envelope math, and that's around 4.7 seconds over MCTP. By the way, there are systems out there that are muxing their I2C packets, and they can't do a 4K packet, let alone a 48K message sequence. So you're not even going to get through it on I2C. So the other interesting thing is measurements, right? Because signatures is all about measurements. Well, we're seeing minimum 5 measurements on most drives. Some of them are going 10. There is a rather large leading silicon manufacturer that is new to leading in the last couple of years that has 72 signatures in their option cards. Yeah, wow, right? Yikes, I never thought we'd see that many. So when you're talking boot time, you're talking like 30 seconds for some of these drives over I2C, if you could even do it, not to mention the 72 signature series. At this point, I'd like to thank OCP for not agreeing on the next generation successor to I2C, because the drive vendors went I3C and the NIC vendors went USB. Now, how am I supposed to plumb a slot, the wires to a slot reliable? Any of you guys been around since the early days? Remember when you had some slots that could handle video adapters and some that could handle storage and some that could handle NICs? My goodness, I don't want to see those days ever again. So, you know, it would really be nice if somebody picked one. I like USB. That's my preference, not DMTF preference up there.
Flex IO yet coming out of PCIe? Oh, shit. We'll give you choices. What was the comment?
The comment has, you seen Flex IO yet coming out of PCIe? It'll give you choices. I already don't like choices. Right? I3C is more expensive. USB's been out there reliable. The parts are cheaper. It's time tested. USB 2.0. You know, give me a nice USB interface. It works for the thingy I stick. If I can figure out how to stick it in my laptop correctly, it works just fine. Yes, yes. Thank goodness for USB-C. anyway, you can see the problem that we're facing here in the control plane now. You'd think, okay, well, there's also PCI VDM. You know, maybe what I do is I do traditional over I2C, and then I do PCI VDM, which allows larger packets, and I do my PQC over it. It's like, I kind of trust you enough to enumerate you on the PCI bus. Let's go ahead and finish. Wait, I got to hold the processor up. Oh, wait, ARM processors don't do PCI VDM. So that's not a solution for everything out there. So, yeah, it's PQC. You know, I heard some rumblings about SPDM going too fast, and certainly we were too late at the beginning, and by the time we got 1.3 out, we were ahead of the industry, well, by 1.2, so we kind of slowed down 1.3, and even then we were ahead of the industry when it came out, and that's fine. You know, it was better to be ahead by a little bit. We figured by about 2 years, so that was why we kind of, all right, let's do all these other things, the bindings. There's an authorization spec we're working on to help our end customers as well as people like CXL that have an auth problem. So that'll run over SPDM as well. No, we don't have a talk on this, but we will have one on, at OCP if you're going to that. You know, we did what we could to get things out when we did. So we got way ahead, though, when it came to the requirements of the internal control plane in the box. And PQC caught all of those people off guard. So if everybody's worried about the signature requirements in 2025, think about what the hardware can and cannot do to help you meet that in that time frame. So call to action, then we got plenty of time for questions. Understand what SPDM means to your ecosystem. It wasn't until last March when I started realizing, because at that point, Sphinx was 56K signatures. They shortened it up a little bit. It was like, oh my gosh. You know, there goes our 2-bit length. Get ready for SPDM for storage. It's really handy no matter which side of the wire you're on, whether you're doing data or management, you're the initiator or the target. It's really handy to have one protocol and only one protocol to cast in silicon and only one set of requirements, especially when you're trying to validate the protocol. And so you're seeing a lot of pressure for SPDM everywhere. So figure out what it means, and then of course get ready for PQC. And if you can help lean on OCP a little bit to pick one management control plane, we'd really appreciate it. Yes?
So how do you see the impact for HDDs that don't have a sideband bus?
So the question is, how do you see the impact for HDDs that don't have a side bus? You've got a mic, so you don't.
Okay. Yeah. All right. Well, so with I mean, that was part of the goal of the transport binding was basically, you know, for especially SAS and SATA, right, there's traditionally no sideband bus. And so, yeah, we have to run everything over the, over really the only bus that's there. Nice thing for those is typically they're behind some kind of controller. So they can be basically held away from the system. You know, in pretty much every case, right, they can be held off, and then, you know, only once they pass, then, okay, we'll actually let data flow.
So we've been beating on that problem since SPDM, right? Because you end up with an island. I can go as far as the controller, but we were hoping for things like MCTP 2.0 or something else to let us daisy chain through it. And, well, validate the controller first, and then let it validate everything else. You know, you could do pass-through if you can trust the controller.
So you've still got a whole bunch of untrusted components in between. You got SAS bridges, you got saddle bridges, you got IP switches and routers and bridges that are totally unknown to your protocol that can do whatever they want in between.
So the question is, gee, what about all that junk in the middle that can do, you know, and you can answer, but SPDM was designed for no entity in the middle attacks. Now, what does that say about the rest of it? You know, it depends if what you're doing and how you're doing those protocols. But at least we can see ourselves safely through the measurements and figure out we can trust the endpoints. And then if you really don't trust your infrastructure, yeah, you could do key exchange and then secured messages. Brett?
Yep. No, I mean, well, yeah, I definitely agree with all that. SPDM was designed to be, to basically account for potential attackers. Also, I mean, you could foresee a world where there's basically a crawl out of the bus where you do have to go hit, say, the switch or the expander, and at least get to active components that are between you and the device.
So one more thing. Redfish has commands where you can go all the way out from our end user down to the device and through the BMC and everything. And so, because some of the cloud providers are they don't even trust their BMCs or platforms.
Yep.
And they crawl everything out by hand. It's crazy, but they do it.
Yes?
Yeah. My question is, what do you guys think about proxies in JEDEC? We're assuming at this point that we can proxy an assembly like a memory module with a single hub that builds a hash of all of the active components on the module and then proxies that so that you only essentially have to implement the full algorithm on the hub device, and the rest can be done by simple serial number.
So the question is, what do you think about proxies and them, I'm going to use the word caching data on behalf of other downstream devices? You want to go first? I have my opinion. Go ahead.
So I would say it depends on your threat model, right? There are physical threats to implementations like that, right? So effectively you're taking the attestation, and then you're not really attesting the device. You're attesting something that's representing the device, which, you use the right term, right? It's a proxy of the device. It depends on your threat model. If you can tolerate that, I know there are lots of systems that ship that, or ship something like that, and it's definitely better than nothing.
Yeah, and go back to the crawl out part of it, right? First I've got to validate the controller or whatever is in front of the rest of everything else. But then again, you're still open to threat models.
I think we can all agree that the industry can't afford to put this level of protection on every device. If you have a DRAM with a 56 square millimeter piece of silicon, and you're going to double that size, the math is never going to work out.
Well,
so I think we're in that position where some level of proxy is going to need to be considered as a part of the solution set.
We have our people in JEDEC, right? You know them, arguing for certain architectures, and they understand the issues too, right? So it's, everybody's got a different footprint that they can handle, and just the buffer space alone to handle some of these message sizes, right, let alone the computational requirements, is astronomical and way beyond what they can afford. So,
and it's getting worse.
Not every island inside the machine is going to handle PQC or need to handle PQC necessarily. Memory, I don't know, but but a fan, am I going to want PQC on my fan? Right? All right, I got a $100 fan in your SKU.
Way back there.
Question in the back.
Yeah.
With regard to your slide set on the storage binding element, I'm not familiar with SPDM. What's the SPDM document that records what the drive is supposed to put in the buffer?
Okay, so question was, what is the SPDM document that states what's the drive supposed to actually put in the buffer? So there's really a couple specs at play. So there is the 286 spec, the binding spec that basically dictates the buffer formats and how they're exchanged. And then there's the 274 spec, which is kind of the core SPDM spec, and that has what are the message formats themselves and what goes in, what goes in every response, and all the rules.
And who defines what the standard measurements are?
Thanks. Well, yes, so that is something that actually falls in the realm of TCG.
Right.
So there are aspects of the solution that are defined out in TCG. So things like how you derive keys and how you come up with your reference measurements, or how you communicate your reference measurements. Right, that's all stuff we've left in TCG's camp.
And then OCP.
And then OCP, that's right. OCP has some additional responsibilities in this. OCP typically talks about requirements at the system level or at the device level. I know there's been a lot of work on, the data center drive standard or something very similar to that term. So there's a lot of drive requirements that come out of there. What else has OCP been doing? Well, safe lock calyptra. Oh.
That's not. So a lot of our standards bodies, SNIA included, make specs with lots of options. And so to me, the value of OCP, at least in the area I play in, is to take a line item veto to that spec and thou shalt do this, don't worry about this, don't do this, do this, Yep. So John Leung, our DMTF VP of Alliances, calls our specs descriptive and their scripts proscriptive. And I like the ways of keeping that straight in my head.
Yep.
Any other questions? We were given the 5-minute warning 3 minutes ago.
I was going to note an interesting observation for a really important component, 4K EEPROM. Those guys were willing to do I2C, but they balked at even implementing I3C, let alone SPDM on top of it.
So the comment was the folks making the 4K parts for things like FRU, they were happy with I2C, but they've balked at I3C, and that's true. DMTF is working on a FRU spec, a FRU update spec, because, and I helped kick that off, we were seeing as many as 18 IOs, sometimes higher than that, to the FRU part. And as you're booting a system, because you got the multi-record format and everybody's got a different multi-record format and all of this other stuff, and you start adding it all up, and the amount of time it takes just to do the FRU discovery was getting crazy. And so you start thinking, well, why 4K? Well, you got to go back to IPMI 20 years ago, and it's like, when we started Redfish, so I was the original architect behind Redfish, and IPMI, they're I'm not going to tell you what they wanted to do. We wanted to match the tool chain out there. And in our factory, we take a JSON document and we turn it into IPMI binary just so somebody else can read the FRU in binary and turn it back into a JSON document. And certainly there are more things to worry about efficiency-wise than that, but it's just plain silly when you start thinking about those kind of things. So my only hope is that new size part, whatever they decide, is just as cheap as that 4K one within a reasonable amount of time. And yeah, it's time to replace all that I2C, It isn't just PQC that's driving it, it's RDE and the rest of it. If you try and go through a GPU and do a full sensor model for all of the Redfish data, you're doing somewhere around 500 IOs on I2C with a PLDM model. Now in RDE, you can turn that down to about 1 or 2. They're larger IOs, but on I2C, that's still a problem for some vendors. It's not for us, but. So there are other things in the industry, particularly if you're trying to get telemetry out of that device, where I2C is just insufficient. So my response to them is, Moore's Law has caught up with you, folks. It still matters at that level, maybe not the CPUs. Any other questions? All right, thank you.
Thank you.